we derived PV equal to RT, we derived the CV equal to 3 by 2R, all these things. Then we also did the diatomic. In monatomic we did the entropy, which is the Sackur-Tetrode equation, which is an extremely useful, as I told you, of when we did it we thought it is not useful at all, but I told you that we are using it every day, like the paper we are writing now on entropy of water, we use this entropy of Sackur-Tetrode equation, that expression we use. Amazing that how that seemingly innocuous simple expression can be used in a very complex situations. That's then we did harmonic oscillator and we got an expression for entropy of oscillation, and that again goes over to the entropy of the specific heat of solids what Einstein and divided, same expression. You know, I am just trying to tell you the reach, that you do one tiny little thing through statistical mechanics. There is no other way you can do that. This Einstein or Debye-Einstein theory of specific heat comes through this partition function. That is what Einstein did. He just calculated the specific heat through e to the power minus half h nu by kBt by 1 minus e to the power minus h nu by kBt square, right. That is, and you have a density of states g omega, then you integrate that. Okay. Then we did entropy and specific heat of that is what by Einstein. Entropy of the vibrational modes also very important. So when I calculate entropy of solid or free energy of solid, how do I do it? Theoretically, I calculate the enthalpy, which I can do through computer simulations, or I can some kind of Madelung constant. Remember the summing over all the interactions if they are charged, and computer simulation we can do that. I take an FCC lattice and I calculate the interaction energy by adding up all the interactions. But then I need the entropy. You would think that entropy of solid is very small, not quite. Entropy of solid may be significant because of the low frequency oscillations and vibrations in many solids. Then you again use your entropy from the harmonic oscillators. Your normal modes are your harmonic oscillators. Okay. That is the first thing you would, solid state physics you learn, like normal modes in a linear approximation. These things go very well with linear response theory, that is very, very important to understand. So free energy of solid, if we want to calculate, we just published a paper, very long paper, 10 years worth of work with my Japanese collaborators, Shinji Saito and Yaomine, and where we tried to get the supercooled liquid and glass, the free energy of the thing and specific heat and entropy, and we use this exactly the expressions we derived here. The entropy, we remove the kinetic energy, then we diagonalize if the disordered thing, we get what is called quench normal modes, and we then use those normal modes to calculate the entropy and the specific heat. And that was came out I think earlier this year or end of last year, probably earlier this year, long paper. Now many people are doing that. So the specific heat and entropy of harmonic oscillator that you learn in the here is used in practical applications in many cases. Then comes the rigid rotator. We did the rigid rotator and we assume it rigid rotator because we assume that rotation and vibration are uncoupled, which we know is not correct because we in undergraduate physical chemistry when you do spectroscopy, infrared spectroscopy, you get PQ or those branches which are because vibration and rotation talk with each other, Coriolis coupling or centrifugal thing that it rotates very fast, then the bond gets stretched or compressed. This the rotation, vibration rotation coupling is a wonderful stuff, tells you a lot of things. Most importantly, it tells you about the anharmonicity of vibration, and that is a very important quantity for our understanding a bond breaking and the activation barrier. All these are very neatly and very succinctly coupled and is a unified concept that we use one side spectroscopy, another side statistical mechanics, another side quantum chemistry and quantum mechanics. Rigid rotator, entropy and specific heat, we do not have a simple analytical expression unless we make low and high temperature assumptions. When you do that, we get expressions, and then when you do the calculations, we find if a molecule like water, the entropy from rotation about 30%. I show you the table that of the A. Okay, but all these things that we did, I am just summarizing and reminding you because they are very important things, were non-interacting limit. I have a rigid rotator, I have a diatomic molecule, I have a monatomic molecule, but they are interacting within themselves. There are intramolecular forces, but there are no intermolecular force. These molecules did not interact. However, you won't have water or your human body unless molecules interact with each other. You won't have a glass, you won't have a crystal, everywhere molecules interact. That is why I quoted Pauli was fond of saying that I created condensed matter, in the means the repulsion were not there, it would not have formed. Crystal, the solid state, the hard sphere crystal, the simple potential is the role, our model of studying solid state or liquid solid transition. So now how do I go about doing interactions? I know the partition function. I know the partition function is sum over e to the power ei by kBt. Today I will give a flow chart, that is what I am talking so much, and then we will do the calculations which are a little formidable. So one of the will be in rigid rotator we found the degeneracy factor, remember 2j plus 1, that was in rigid rotator, you have done in quantum mechanics. Harmonic oscillator, the atomic, this Gi equal to 1, particle in a box, Gi equal to 1, right. Okay. Other way to do is classical. This indistinguishability Boltzmann put by hand, and this is the one that we know after doing quantum. The best way to think about it to get this factor is to do the quantum and then come to classical from quantum, which is an exact way of doing, and you find that you must have that. This is other way there, you can have a conceptual saying that okay, this is normalization of the volume of a cell, but that kind of thing I do not particularly encourage. I would rather say do the quantum and then come to classical. So and the Hamiltonian, this is the total Hamiltonian kinetic energy and potential energy, okay. And this quantity U is the, many times we do not write all these things, we just write ij here and we put a prime here. That is the StatMech people standard notation. We just do that, then we do not have to write all this. It is understood. So we are further assuming that interaction there is a two body interaction, means we are saying that if I have 3 particles 1, 2, 3, then this interaction is sum of pairwise interaction. That could be a 3 particle interaction also, which are important in some cases, but understanding much of condensed matter physics, we do not need this 3 body interaction. That is a fine tuning. We need sometimes, but like doing a liquid silicon, we need the 3 body interaction, but much of the time that because when you are kind of near metal or metalloid kind of things, then 3 body and many 4 body interactions play important role. So now there is this popular saying, get the bull by the horn, and means you have to do these complex things, this integration, where in a classical thing we can do the momentum integration because it's uncoupled, there's a bunch of Gaussians, I do not need to write that, I will be cavalier about it because I know how to do it. So basically this is the thing I need to do. So again if I need I will put them back, I do not care about them. So I will write Zn by n factorial, I will not write the other thing 1 over n factorial. So this is the configuration integral. I have taken out the momentum part. You understand that I have integration over beta h, beta H Hamiltonian has kinetic energy and potential energy, they are uncoupled. The potential energy part, kinetic energy part pi square by 2m, they are nothing but Gaussian. And not only that, I and j are uncoupled, x, y, z are also uncoupled. So I can do the 3n integrals, and then I get lambda to the power, lambda is the de Broglie wavelength, 3n by 2. That's the partition that I am not writing, because that's the part which gives you Sackur-Tetrode equation and PV equal to NKBT, ideal gas. But right now I am not interested in that. Many times when you do the free energy, we write free energy A equal to A ideal plus A excess, and A ideal, because this is free, the ideal part comes as a product here, correct? You understand that now, because it is e to the minus beta h and is the exponential, so that become product. Then I take the log, free energy is log of partition function, and then the product comes out separately, that I call ideal. A ideal is the ideal gas free energy, which we did, and this is the excess part, and this is the interesting part. This is the part we are now trying to do. So this part comes from the interactions among particles, and which is highly non-trivial. I will go back and forth. I will use this a little bit, then I will go back, because I want to give a flow chart. I want to tell you how the thing is done, so that you get the big picture, and then doing the equations is filling this big picture. But going directly to the details does not help if you do not get the big picture, because it is the big picture that will stay with you, the understanding. The details will be given in books which I always look up, okay. That is the way actually to do any interesting stuff, okay. So we did this here, this and this is the interaction potential we discussed at length, and this is the pairwise interaction potential, this is the total potential energy. And as I just discussed here, this is the quantity, and I said I do not care about this part, because this part is the ideal gas part. So when I take the log of that free energy, I get, and then I get everything from the Helmholtz free energy. The reason we work in canonical ensemble is because I get entropy and pressure by taking derivatives, okay. It is far more complicated in getting in grand canonical partition function, and doing of course is very difficult, because you no way to go unless you do particle in a box, but then in other systems with continuous potential you have no way to go when you go to microcanonical ensemble, okay. So this is the thing then. So as I said before, that this comes in the exponent u, and u is a sum. So I put that sum here, then when I put this sum here, this is like that. Then I realize that this quantity is nothing but product. The sum here, this sum comes out as a product, okay. And then I looked at this integral, and I had to do this integral in a very difficult way, because two things, this integral, first this potential is fairly complex, and to make it worse, this potential goes to 0 when separation between two particles I and j becomes larger, which indeed it should be, it should go to 0. But that creates the problem is that I have to do this integral, and if I do that integral, then that integral goes to 1. You do not want that, you do not want the asymptotic part goes to 1, you want that asymptotic part goes to 0, okay. And that is what Mayer did. Then it saturates the unity, and that becomes hard, so partition function fails to converge, also difficult to do. Then introduce Mayer F function. So Mayer F function is the following function. If this is the, so the quantity that comes is e to the power minus beta u, this quantity, that is the one we are dealing with, that is the beast. And why it is a beast? Because this, if the simplest interaction potential is that. So there are two parts of the interaction potential. One is this part, which excludes particles, volumes, excludes certain regions of the configuration space to my particle, because they are interacting and they are harshly repulsive at short distance. Then however, other than that, it has an entire volume to itself. That part comes from here. Okay. So, he then considered this, he said, okay, let me introduce this function f, and that then is like that. His own sole idea was to make it go to 0. So, now it goes to 0, all right, and this is my sometimes we call it exponential bond, because to a chemist these are essentially bonds, they are interacting. They are not chemical bonds, but we call them physical bonds, but this has become -1 now. Now the advantage is that if I put this into there, I will get this kind of terms. Now it has becomes, I can decompose it into smaller parts. That's the important thing. Before I could not do anything, like I can do something. Okay. So then, as we discussed the other day, this is the decomposition I did with 3 particles. Then the first one is I put it here, sum over one term is the first term is the 1, second term is the 2 particle term, next term is the 3 particle term. So one part is just a dot, no line. Then the second is the bond, FIH is the bond that connects these 2 particles. Then this has the 3 kinds of, then 4th like that. Total number of particles in the system is, so ml, now we say okay, ml is the number, total number of molecules in a cluster of size L. So cluster of size 2, how many total number of molecules? 2. Here 3. So now, however, so instantaneously at a given position, like in this room, I have oxygen and nitrogen, and say I have n number of them, and let us consider only nitrogen. So I have n number of nitrogen, and now any times they are mostly dispersed in the room, but now and then they come together and they form clusters. There are clusters of diatoms, there are clusters of triatomic, there are maybe little bit more of that. Okay. Much of the time I can describe this room by the function F12. At most they are diatomics, you know. But you understand that whenever one is coming under the sphere of interaction of the other through interaction potential, I draw a bond. But these bonds are flickering bonds, they are breaking and forming, because as molecules coming together and going away. Okay. And but the instantaneous state of nitrogen in this room is given by the ml. You know, and as we are talking, and if there are n number of nitrogen molecule, then M1 is 90% of that. Okay. And then 8 of the 10%, another 90% are this one, binary interaction, and a small number will be ternary interaction. So you immediately see, if I want to describe the nitrogen in this room, I won't need the ternary term that much. I can see, beginning to see an approximation at the low density that I can do with ideal gas plus a correction, and that correction is the F12. Now I go to denser gas, I go to nitrogen a little bit denser and then to liquid, then I will need all the terms, but I have a systematic way to add them. This scheme will not work all the way, but its scheme will take us far, and then a different theory takes over. Okay. But it is the beginning. Now we defined the cluster integrals called Mayer cluster integral, which are in a given class, a class is characterized by L. We are not making a distinction between this and this now. We can then consider all these clusters. Now what are the clusters? Just in Feynman path integral anywhere, these are nothing but this general language of physics which started 1937 Mayer's paper. These are nothing but integrals. So when you say graphs in physics, they are integrals. Okay. And then this is the most powerful language in many body physics. In chemistry, we use it in theory of liquids. Even these people, the quantum chemists, they do these T operator expansion, all these the different things essentially they have e to the power t and very similar things goes on there. So, there is certain universality and understanding all these things. You understand one, you basically know why one is doing this. So, this is then we can now calculate the okay, but the dot first one is this quantity B1, B2 is this quantity and B3 I sum over everything. Remember that these are these three and last one, the formidable one is this one. I can go on writing like that. So, these are the may are introduced and this is cluster integrals. It is called reducible cluster integrals because these can be further reduced into this part and this part. Okay. This is called irreducible, we will handle, we will deal with there and this is reducible. Okay. But this can be explained in terms of this one. Okay. Now, next what Mayer did, okay, as I told you that we are going to divide and conquer, we had full partition function, we are reducing this total partition function into the cluster integrals. Then we will reduce the cluster integrals even further called irreducible cluster integrals. Then you will see under certain approximation the irreducible cluster integrals are nothing but virial coefficients. Suddenly you see, oh, I can now have at a some limit this beautiful, this rather complicated theory, though beautiful, we can connect it to experiments. And you will see that that's really very, very nice. Okay. Now what we did? We have to now find out what is the decomposition. Decomposition, I want to express the partition function in terms of this reducible cluster integrals. How do I do? I know ML is the number of clusters of size L and then I say okay, and this is my definition. And remember that this is kind of a normalization factor put in here. L factorial because the number of ways I can arrange, two factorials will come, one is L factorial and is ML factorial, and as I was saying this is the kind of things looked into from the multinomial theories or the way you can arrange the particles in a box and you name the box 1, 2, 3, 4 like that, and this is my L, the number written on my box is L. So, when I have 2 particle cluster, I put it L equal to 2. I have a 3 particle cluster, I put L equal to 3. Now, each of these L equal to 3, I have the 3 particle clusters and number of 3 particle cluster in my box label 3 is M3. Okay. And this is the way one does exactly this problem is done in combinatorics. Okay. When you do that, this is because what is the configuration integral of that? This is just this thing because ML of them, okay, and this is the weight. So, this part is trivial, right? Okay, little less trivial is total number of ways we can combine them. I have n of them into groups of L, and this is the distributed in unnumbered piles of L objects. This is the quantity. So, the total partition function is the product of the two. When you do the products, there are certain cancellation, L factorial gets cancelled, ML factorial survive and VBL to the power ML. And this is the beautiful expression is the called, it is exact, used also in quantum, it is called Mayer R-cell cluster expansion. So, this is an expression of the partition function. It has certain advantages, certain disadvantages, but whatever it is exact. So, this is called decomposition. It is so beautiful, let me write it down. Okay. So, this is the quantity I wrote down, and the way to work with this exact partition function is to consider what you call thermodynamic limit. We have to take n going to infinity, v going to infinity such that n by v rho equal to constant, alright, that the limit we will take. We will ignore this for the time being, we will come back. Okay. Now, something very interesting, how did Mayer go further and derive two very important things which we call cluster expansions. One is the density in terms of LBLZL. I will come back, but I just want to mention this too. We can derive it from canonical partition function also. Another thing is the pressure in terms of BLZL. I am giving you and then come back. And so these things that will derive now. So look at the beauty, density is L, BL, Z, where is the fugacity, which is done just like beta in canonical ensemble, beta become 1 over KBT. How did beta enter into the description in canonical partition function? Yeah, absolutely, Lagrangian multiplier. Here also, what is the constraint? This is the constraint, and that constraint enters through Lagrangian multiplier now. Beta enters through which constraint? Energy, exactly. So, and temper and energy are conjugate quantities, right? So, here what is the conjugate of number? Absolutely. And then this is e to the power mu by KBT. So, fugacity is just beautiful, these things are. So, I have an expansion, I will derive in a minute, density in terms of cluster integrals, and now I have little bit more work, I get now pressure, another equation I will derive is these things. I told you I will give you a flow chart. So, I have an expansion, these are called cluster expansions, they can be derived also through a canonical partition function, but that does not have the physical picture it has, okay, Mayer's theory. Now, I now give you two expansions, one is density in terms of fugacity, then I give you another pressure, is the equation of state. Now, if I give you two series and I tell you to eliminate this, you have done in your class 11, eliminate fugacity, give me an expansion of pressure in terms of density, okay. I give you everything, I give you all the coefficients. I have not told you how you are going to calculate them, I will tell you that. But I can eliminate, like I have given two series. One series is density in terms of fugacity, other series pressure in terms of fugacity. Now I tell you, eliminate fugacity, give me a series of pressure in terms of density. This is possible, so long both these series are convergent. Right? When you do that, you get the virial series. That is the thing I kind of jumping and telling you. So, what is the flow chart now? We start with the partition function, we are getting a decomposition, which is the cluster decomposition and exact partition function. In terms, so we form earlier on, you go to cluster integrals, then I get a partition function, then I get two expansions, which I eliminate and get the fugacity. That allows me now to get the coefficients of cluster integrals, and we will do that. The way one works out with this equation then is that we will do again the same game as we discussed, we will take a maximum term method. There is a principle of statistical mechanics, it turns out that when you have, see ML is a distribution of distributions. Please try to understand it, distribution of distribution. Why? As I said in my nitrogen example, there is any time ML, the number of particles of number of clusters of size L, that is a distribution. However, as this is continuously changing, there is a distribution of distribution. Okay. Now, however, there is one distribution which maximizes the partition function, and that is called maximum term method. It is a already very well established method in probability theory. maximum term method. So, we have to find the maximum, that particular set of ML, I call it ML star, which maximizes the partition function. And one can now show by mathematical analysis, in the limit n going to infinity, the maximum term method dominates. So, there is a distribution, that is the reason a system is stable, that is the reason free range is minimum, it is all tied together. So, now you can easily do a maximum term method. There is a huge amount in Wikipedia and all these things in probability theory, because it is used in probability theory. Yes, Subhashish. Yeah, exactly, very good question, excellent question. We implement maximum term method through Lagrangian multiplier. Whenever we are doing maximizing or minimizing something subject to a constraint, so the maximum term method is general method which you used even before, but Lagrangian multiplier is the way to implement that. Whenever you are finding extremum of something with a constraint, extremum means you did d alpha, that quantity is 0, but you want to do it with a constraint. If you do not have the constraint, it will give you everything. The constraint is done through Lagrangian multiplier, and that introduces one undetermined coefficient which we appeal to physics or experimental or our physical A and get what is the undetermined multiplier. Like we found out through thermodynamics, beta is 1 over kBT. Okay. So, this is what I have been talking of the flow chart, that there is a grand scheme that is going on, and we need to appreciate the grand scheme, that how the whole thing is unfolding.